by adopting new design and process. First, we have upgraded the switch of the transformer and introduced a gallium nitride, that is GaN, high-frequency switch, so the transformer can operate at a higher frequency. Our prototype has once operated at 800,000 Hz. Higher operating frequency, less winding, better PCB winding process, all result in a smaller size of the transformer. These are all significant improvements. We also use GaN to drive the transformer to a higher frequency. It's a breakthrough that we've been dreaming for years. In the past, we used the MOSFET for the switch, but this traditional material are not suitable for the high-frequency switch. On 50-watt mini SuperVOOC charger, we used the gallium nitride. Only this material will stand the frequent wear and tear. Based on the gallium nitride switch, we took a further step. We developed a brand new active clamp flyback, that is ACF architecture, and introduced ZVS. Before turning on and off the switch, it will clean up the voltage and current in the circuit, so the wear and tear on the switch is reduced. The traditional transformer of a 50-watt adapter is more than 20 mm thick. As for our mini adapter, the transformer is only 8 mm thick. That's over half of the thickness saved. We have also integrated power semiconductor devices on the PCB of the planar transformer, achieving a higher level integration. In one word, on the basis of the GaN and a brand new ACF architecture, we have developed a mini planar transformer with our proprietary tags. The next thing to go for is the electrolytic capacitor. Take a look at the PCB of a traditional 50-watt adapter. You will see from the picture that the biggest component is the cylinder here, accounting for about a quarter of the PCB. This is an electrolytic capacitor. It ensures constant, stable output of energy. When you plug the adapter into the socket, it is powered by 220-volt AC, which is not a steady flow. We need an electrolytic capacitor to store the energy in advance, and then generate a steady flow to the battery. It works just like a reservoir, which stores water and controls how water flows through downstream waterways. Electrolytic capacitors have been put into use for nearly a century. The solution is quite mature, but the problem is the size gets bigger as the power increases, which leads to a bigger size of the charger. For example, a 125-watt charger will be larger than a 65-watt one. Now, to make the charger smaller, we must get rid of the electrolytic capacitor. Compared with traditional adapters, the PCB size of a 50-watt mini SuperVOOC charger is reduced by 52%. This is our breakthrough, non-electrolytic capacitor design. I'm 100% confident to see we are the first phone vendor to use such a design and make it available for mass production. To ensure the safety, the adapter is equipped with the expensive clamping diodes. This is a first in the consumer electronic industry, as clamping diodes are traditionally used in the aerospace industry. They can effectively absorb surges, and the adapter will handle all the voltage fluctuation from the power grid and deal with the surge so as to ensure the reliability. Fun fact, as it's an industry first to use clamping diodes, when we talked to a supplier, we nearly got rejected. because in the beginning they found it hard to believe why a phone vendor would purchase such expensive and high-standard components. They were worried about our BOM cost. The non-electrolytic capacitor design has a feature. The energy it generates for the battery is discontinuous. Will that work? Well, as early as MWC 2016, we unveiled the concept, low voltage pulse. As you will see from the flow here, compared with traditional adapters using electrolytic capacitor, pulse charging has a discontinuous 100 Hz flow. The flow